Hello. In the previous video, we have defined the group and we have given some examples of groups. So here we will define another type of group that's called commutative group or abelian group. So the definition is a group G with a binary operation star is called commutative group or abelian group if for all xy belongs to G, we have x star y is equal to y star x. If this property satisfies, then we say that the group with respect to the binary operation star is called commutative group. What's the property? X star y is equal to y star x. What does that mean? Either you operate x with y or you operate y with x, you will get the same answer for every pair of x and y in the group G. If this is true, then we say that the group is commutative. For example, in the previous video, we discussed some types of groups. So if we visit those types, we will check whether those groups are commutative or no. So suppose our group is the set of integers with respect to the binary operation addition. Then we will check whether it is commutative or not. What do we have to do? We have to take any two elements from the group. Here the group is Z, the set of integers. And we have to check whether if I add x and y or I add y and x, can I get the same answer? So let's look. Here, let's choose m and n from the set of integers. Then we know m plus n is equal to n plus m, because we know in the set of integers either you add this integer with this or you add this integer with this in this, you will get the same answer. So for integers, we know this property holds true. For example, if you take 6 and 5, what will you get? 6 plus 5 is what? 6 plus 5 is 11. What is 5 plus 6? 5 plus 6 is also 11. This means this sum and this sum are equal. Therefore, we say that this is not only true for 6 and 5. This is true for any two integers coming from Z. Since you know what is Z, let me recall. Here, Z is the set of integers 0 plus minus 1 plus minus 2 plus minus 3 up to so on. What does that mean? Here you have 0, here you have plus 1 and minus 1, here you have plus 2 and minus 2, here you have plus 3 and minus 3. So you have every number and its negative in the set of integers, right? So that means if you take any two integers from the group m and n, if you add them this way or you add them this way, you will get the same answer. This is what we claim, and this is true for integers. Since this is true for integers for any two numbers in the set of integers, therefore we say set of integer is a commutative group because this property is satisfied. Okay? Similarly, you can prove that if we take the set of rational number with respect to addition, if we take this group, this is also a group, right? In the previous video, we have proved that this is a group with respect to this binary operation, right? So if we take this group, this is also commutative, okay? So it is also commutative. Why it is commutative? Because if you add any two rational number R1 and R2 this way, or you add R2 and R1 this way, you will end up with the same answer. Okay, so this is true for any two rational numbers also, right? So I'm not gonna prove it, it's very clear from the context. Similarly, if you take the group of real numbers with respect to addition, so this is also commutative group, because if you add any two real numbers L1 and L2 this way, or you add L2 plus L1, you will end up with the same result in both cases. So this is true for all real numbers. So that means set of real numbers is a group with respect to addition, is a commutative group actually. What about the set of natural numbers? Here is another example. Let's look. What about the set of natural numbers? Can we say that this is a group? Well, let's check, is it a group or no? So, what is a group? A group is a set with a binary operation defined on it such that four properties satisfied, right? So, we will check the first four properties are satisfied here or no. So the first property is, if you add any two natural numbers, if you take any two natural numbers, for example n1 and n2 from here, what will happen? If you add n1 and n2, then the closure property says, or the inner property says, if you add any two natural numbers, it should be inside the natural numbers. Is it true? Yes, of course it is true, because the set of natural number is 1, 2, 3 up to so on. If you take any two numbers from here and if you add them, for example, here you have 20, okay, here you have 3. So if you add 20 and 3, you will get here 23. That means if you add any two natural numbers in this set, you will get a new natural number which will be somewhere in the coming integers, right? So that means the first property is satisfied, so this is true, no problem. What about the second property? The second property is n1 plus n2 plus n3 is equal to n1 plus n2 plus n3. They are equal or no? The second property says if they are equal, that means the second property is satisfied. So look, if you add any two real natural number here and then add this natural number, or you add these two natural number or then add this one, you will get the same answer. Because for example, if you take 6, 5 and 3, if you add them first, or you add 6 and 5 first and then 3, okay, look how we solve them. 5 and 3 is 8. Here 6 and 5 is what? 11 plus 3. Although these terms are different, but if you add them, you will get the same answer. Look, here I have 14 and here what I have. So both sides are the same. So this is not only true for 6, 5 and 3, this is true for all natural numbers. So that means this is indeed true. Okay, let's look at the third property. The third property says there is an identity, right? So with respect to addition, we will check whether there is an identity or no. In the additive group, the identity, we consider that the identity is 0, right? Since if you add 0 to any number, you will get the same number. What does that mean? That means this is a number which does not change the shape of any number. So you had the shape of n and you get back the same shape. That means this is the identity. it doesn't change the identity of any number. So that's why it's called the additive identity. Similarly, the multiplicative identity is 1. That means if you multiply 1 with any number a, you will get back a. That means 1 doesn't change the shape of any number if you multiply 1 with any number. So here we will check whether this identity is in the set of natural number or no. Since the set of natural number is what? 1, 2, 3, 4, 5 up to so on. So can you check whether the zero, the number, the identity is inside or no? Of course, if it was, it should be here. That means 0 is not inside the set of natural number. Okay? 0 is not inside the set of natural number. So n has no identity, right? Because the additive identity was 0 and 0 is not in the set of natural numbers. So that means n doesn't have identity, right? Oh, that means this property is not satisfied. Therefore, n is not a group. So if something is not a group, then we cannot talk about the commutative group. If it was a group, then we could talk about the commutativity or no. So if it was a group, then we could check the condition for the commutativity, but now we will not check because it's useless, because commutative is strongly belonging to the term group. So if something is not group, that means we will not go for commutativity. So previously I have given you some examples of additive groups. What are the additive groups? I am going to recall those examples. Actually here, all the examples which we have discussed previously for additive groups, they are all commutative additive groups. The first one is Z with respect to addition, then Q with respect to addition, and R with respect to addition, and then the set of complex numbers which we have already studied in the previous chapter. So it's also a group with respect to addition. Another very interesting group is just this set. It is also a group because it trivially satisfies all the properties. So it is also a group with respect to addition. So I should write with respect to addition. So this is a group. With a group of single element is called the identity group, right? It is also a group with respect to addition. So they are all commutative additive groups. Now we talk about some multiplicative groups. So why I called these additive groups? Because they are groups with respect to addition. So when I call a group with respect to addition, that means you have to add elements inside the group. You will not multiply or divide the elements inside the group. Okay. So similarly, there are some multiplicative groups. So if we talk about the set of integers with respect to multiplication, normally we write this dot for multiplication. Okay. So this dot is for multiplication, right? So we will check whether it is a group or no. We don't know right now. We will check the 4 conditions of group, but this time with respect to multiplication. So the next example is the set of rational number. We will check. By the way, this is a group with respect to multiplication. This is a group. I'll not solve it. Okay, if you want to check that this is a group, you can check the 4 properties of a group, whether they are satisfied in this group with respect to multiplication. You will easily check that this is a group. I will check whether this is a group or no. Similarly, there is another group. There is a little mistake here. So set of rational number is not a group, but if you subtract 0 from the set of rational numbers, if you take out 0 from the set of rational numbers, then it is a group with respect to multiplication, right? Similarly, if you check the set of real numbers is not a group, but if you take out 0 from the set of real numbers, then with respect to multiplication, it's a group. Look, I don't know whether this is a group or no. I will prove it, but this is a group. Okay, so set of rational number is a group without 0, right? Similarly, the set of real numbers is a group without 0 with respect to multiplication. Similarly, the set of complex number without 0 is a group with respect to multiplication, right? So I will prove that this is not a group. Actually, I'll prove that this is not a group. Actually, this is not a group. But I wanted you to check whether it's a group or no. So I'll prove it that it's not a group. This is a group, this is a group, and this is a group. I'll check one of them. So I will check whether this is a group or no. You can check this and this. So let me check it's a group or no. There are 4 properties for the group. So I will check one by one. So the first property is closure property or inner property. So that means if I take any 2 integers, so the first property is inner property, inner or closure. That means so if I take any 2 integers, let L and M are 2 integers, then I will check L times M is also integer. Yes, of course, it's an integer. This means L times M, the product of L and M. So, what does that mean? Since here you have the set of integers, which is 0, 1, 2, 3, you could write it plus minus 1, plus minus 2, but I'll write 1, 1, 2, 3, and here minus 1, minus 2, minus 3, both are the same shapes of the set of integers. So what will happen? If you multiply this minus 2 with 3, what will happen? Minus 2 times 3. What will you get? You will get negative 6. So negative 6 will be here. So here you have minus 1, minus 2, minus 3, minus 4, minus 5, up to so on, minus 6. So minus 6 is inside. So this is true for all 2 numbers. Whenever you take any 2 numbers from this set, if you multiply, you will get the resultant number either on this side or on this side. That means the inner property is satisfied, okay, for the set of integer with respect to multiplication. Let me check the associativity. What's the associativity? If you take L, M, and N from the set of integers, like any 3 integers from here, so the associativity means if you multiply L after you multiply M and N, or you multiply first L with M, then you multiply the resultant with N, you'll get the same answer. It's very clear from the context because all of them are integers. So the associativity holds. For example, if you take 3 times minus 2 times 3, for example 5, or you write 3 times minus 2 times 5. What does that mean? Here I multiply these first and here I multiply these first, but I will get the same answer. Look, if I multiply these first, I will get negative 10 inside. If I multiply these first, I'll get negative 6 inside. Here I have 5. What's this? This is negative 30 and this is surprisingly negative 30. So they both are same. What does that mean? This means if I take any three integers and I multiply this the way or this way, I'll get the same answer. Okay, so the associativity is also proved. So look at this third property. The third property says there is a multiplicative identity, right? If you check in this set, you have 1. Since we know 1 is multiplicative identity, because if you multiply 1 with any number x, you will get the same number x. That means 1 doesn't change the identity of any number. It doesn't change the shape of any number with it multiply. So that means 1 is multiplicative identity. Since 1 belongs to this set, so I can say that 1 belongs to this set because I can see 1 here. So since 1 belongs to this set, therefore identity is in the set of integers. Since 1 is multiplicative identity and 1 belongs to this set, so Z have identity, right? Okay, let's check the last property. The last property says that the inverse of each element should be inside the set. The last property says if you have a number, then its inverse must be there. Okay? So for example, if you have 3, what is the multiplicative inverse of 3? There are two types of inverses. One is multiplicative and the other one is additive inverse. But here we are talking about the multiplicative group because we are talking about that Z is multiplicative group. We are checking. So we will check whether it has multiplicative inverse or no. So what is the multiplicative inverse of 3, for example? The multiplicative inverse of 3 is a number. If you multiply 3 with the inverse, you'll get identity, right? So what should I write here? So the obvious answer is 1 by 3. Because if you multiply 3 with 1 by 3, you will cancel 3 with 3 and you will get 1. What does that mean? This means the multiplicative inverse of 3 is 1 by 3. But 1 by 3 is not here. Here you have only the integers which have no fractions. But 1 by 3 is a fraction of two integers. So the inverse of 3 is not here. Similarly, the inverse of 2 is not here because the inverse of 2 is 1 by 2. Because if you multiply them, you will get 1. Similarly, the inverse of negative 2 is 1 by negative 2. If you multiply them, you will get 1. So, no element has inverse except minus 1 and 1. So it is enough to find only one element, but here many elements doesn't have inverse. So I'll write since 3 has no multiplicative inverse. So since the multiplicative inverse of 3 is 1 by 3, but 1 by 3 is not in Z, 1 by 3 is not in Z, therefore the last property is not satisfied. Since the last property is not satisfied, that means Z with respect to multiplication is not a group. Z with respect to multiplication is not a group. Since it's not a group, so therefore we will not talk about the commutativity, but you can check these properties for multiplication of multiplications for these groups, right? You will check whether this is a group or no. You can do an exercise. You can check whether this is a group or no. You can check whether this is a group or no. And then you can talk about their commutativity. In fact, these are commutative groups, right? So you can check whether they are or no. Normally, we write this group in this way, Q0. What does that mean? This means Q is a group with respect to multiplication, but if you subtract 0, if you take out 0 from the set of rational numbers, just like this way. Similarly, this group can be written as this way, R0. That means R is a group with, so R without 0 is a group with respect to multiplication. Similarly, this can be written as C0. That means C without 0 is a group with respect to multiplication. So please pay attention that when we talk about the groups with respect to multiplication, that means we always take out 0. But if we talk about the groups with respect to addition, we don't take out any element, okay? We don't take out any element with respect to addition. So this is the main difference in the additive groups and the multiplicative groups.